So we're moving on to part 2 of the VAT photopolymerization lecture. In part 1, we got all the way up through stereolithography, and now in part 2, we're going to tackle digital light processing. Okay, so digital light processing is another VAT photopolymerization process. So we're still going to be taking a vat or reservoir of liquid photopolymer, exposing it to some light source so that we can solidify it. And that's how we're building our model. The DLP process, or digital light processing process, is going to be a bottoms-up process. Okay, so we're going to be building the part essentially upside down. The light source can be any light source, right? But it's going to have to be, it's not going to be a laser. Let me say that. It's not going to be a laser. And it's going to use what's called a DLP chip. And we're going to talk about that in a second. That's kind of the whole basis of this. Remember that the DLP process, as well as the clip process, which we'll look at later, is going to be a mask projection process. So it's going to flash and solidify the entire layer instantaneously, as opposed to the SLA process or the VSPS process, where we use a laser to trace out the layer. So this is going to be one of the faster processes here. It's predicated, the DLP process is predicated upon using one of these DLP chips, as you can see in the upper right-hand corner. So these chips were used basically as projectors, or in projectors, I should say. They were developed by Texas Instruments, and they're repurposed here for creating 3D prints. The DLP chip right here, this chip right here, contains 8.8 million hinge-mounted micromirrors. Now, I know this kind of boggles the mind that all of this whole surface right here is made up of 8.8 million micromirrors, all right? And each one of those mirrors is on a hinge. And you can see that this middle figure here is a great enlargement of that. And you can see this is one of the mirrors, and you can see the hinge mechanism underneath. So some of the mirrors have been removed so that you can see the hinge mechanism. And basically, if we look over here on the right-hand side, this figure, it's showing what's going on. Okay, so these mirrors are basically going to turn one of two directions. They're either going to turn away from the light or they're going to turn towards the light. And so that allows this chip to control whether one mirror or the other shows light or shows blackness or the lack of light. And so that's basically what's going on here. Okay. It's not a very complicated idea, right? You're either going to allow light to reflect or you're going to turn the mirror so that light can't reflect. But the fact that we can put 8.8 micro mirrors on this small of a surface, and each micro mirror has a hinge essentially in it, kind of gets to the boggling the mind part here. So how does the DLP process work? Well, here we have the projector, which is going to provide the light source. In this case, the light source is not a laser. It's just a UV light, a regular light, okay, like a light bulb light. The build platform is going to start at the bottom of the reservoir, and it's going to be lifted up. It's not going to touch the bottom. It's going to be lifted up off the bottom equal to one layer thickness, all right? The light is going to be shined on the build platform through the photopolymer resin, but it's going to be shined through the DLP chip. So basically, the chip is going to only illuminate the area that we need to solidify. All right, and then the build platform is going to continue up one layer or one level. And then the next flash will occur, and then the platform will move up again. So it repeats in a bottom-up process of building. All right. Now, I have a couple of videos to help explain how this whole DLP chip works. So we're going to watch these for right now. And in the first one, it's this gentleman is going to make a larger model, essentially, of a DLP chip so that you can kind of see how it's going to work. Now, in some of this, this is a long video, so I'm going to fast forward through different parts just so we can get to the parts that we really need to.
Today on Applied Science, I'd like to talk about how digital light projectors work. And so to demonstrate this, I made a macro scale digital mirror chip, which we'll have some fun with. And then also we'll zoom way in and check out what an actual DLP chip looks like under the scanning electron microscope. Okay, so let's get started. Almost all projectors work on the same basic principle. You start with a light source, you filter the light source based on the image data that you want to display, and then you use a lens to transfer that image from within the projector out to a projection screen. So in a film projector, it's pretty straightforward. We've got our light source, you pass the film in front of it, and then you use a lens to transfer that image to the screen. And in an LCD digital projector, we'd have basically the same thing, but the plane of the film is replaced with a liquid crystal, which allows the light through in certain areas and not in other areas. So we have pixels that are clear and pixels that are opaque. One problem with liquid crystal display projectors is that you sometimes need 3 separate LCDs for the colors.
All right, I'm going to fast forward it here because we don't need to talk about the projector as much, and we can talk more about the chip.
A bulb, and this is a high-intensity discharge bulb, like a mercury vapor lamp, and then a lens to get the light in a nice column from this light bulb, because normally it's just spraying out in all directions, but we want to have a column of light on this special DMD device, and DMD stands for Digital Micro Mirror Device.
This is the DLP chip right here.
I should note that DLP stands for Digital Light Processing, which is a trademark name, kind of like Xerox. It's become a very common way to describe this, but that's actually a trademark name owned by Texas Instruments. And the digital mirror device is an array of tiny mirrors, and when the mirror is facing in the right direction, it shines light through our main projection lens, and then it forms an image out on the projection screen here. So it's basically the same thing as an LCD, but instead of the pixels being clear or opaque, the pixels are either a mirror that's turned in the right direction to shine light through this, or they're turned away so that the light doesn't shine through the lens. I owe a big thanks to Mike's Electric Stuff for donating this DLP chip to my channel here, and I cracked it open. This is actually what the case looks like, and I opened it up, which took quite a bit of doing. Originally I thought that the case was soldered shut, but it's actually been welded, and so I ended up using a Dremel just to grind away the casing here and opened it up. And this is what the chip actually looks like. So as you can see, it just looks like a continuous mirror, but actually there's many, many thousands of tiny little mirrors that represent 1 pixel each on the surface here. So to get a better understanding of how this works, I made a macro scale model. So let's take a look at that. This is a model of the digital micro mirror device that's in the projector. And as you can see, it's built with a whole bunch of individual mirrors. And just like in the real DMD chip, each mirror has its own little hinge. And so I built this by starting with a plastic grid and hot gluing down some thread across the grid openings. And then I cut out a whole bunch of small mirrors from a piece of mirrored acrylic and glued those down with a washer on the back. And the original plan was to make tiny little magnets, electromagnets, winding them on my lathe, and then putting an electromagnet behind each mirror, and so then I could move the mirror with an electromagnet. And I did actually get this working. It drew about 300 milliamps, I think, at 3 volts or so to get the mirror to move. However, I scaled up the effort mentally required to do this for, 16 or 25 or 36 mirrors, and it wasn't going to happen today. So I came out with another way of showing this that's a whole lot easier. Here's all the washers on the back of each mirror. I can affect them all globally just by using a really big magnet. So it's true I don't have image control. Originally I was going to have a microcontroller actually control the electromagnet so I could generate a primitive image.
Okay, so I think that's all we need to see here in how the DLP chip or the DMD chip is going to control the mirrors so that they either reflect light or they don't reflect light. So you either have light or you have dark. And that's how we're going to recreate our image And the image that we're recreating in a 3D printing sense is each individual layer. Okay, so this process is done layer by layer as we build the part. Now let's look at another video. This is actually the Ember machine that we have in our Moraine Valley Community College 3D printing lab. And these gentlemen are going to talk about how this part works. And again, I'll fast forward it through some of the parts that we don't need to listen to. All these videos are available on the class website, so you can watch them in their full entirety if you so wish.
Coming up, Ember 3D printer. Right, today we're taking a look at the Ember 3D printer from Autodesk. We've been printing our projects for several weeks and wanted to share some of the workflows and techniques. This is a DLP SLA 3D printer, so it's completely different than all the 3D FDM printing we've been doing. So here's a basic look of how it works. So this printer uses a DLP projection to cure photosensitive resin using a UV light. The projector shoots UV light as one full slice for each layer, and this can print in resolutions of 10 microns. So the metal build plate moves up along the Z-axis and prints emerge from the resin tank. The Ember printer uses a cure and peel technique. This is where it exposes and separates for each layer to create a high definition part. So when the UV light is exposed to the resin, it's hardened and solidified. The resin tank then separates and moves away from the build plate and then returns for the next layer. And this does this for like every layer. Enclosure parts that are smaller than 30 millimeters can actually print without any support material. STL models themselves are going to get prepared using Autodesk's mesh mixer, and here you can set up your support structures to hold onto the models to the print head. So setting up the proper orientation for an object can be a little tricky. You'll want to test different angles to get the right orientation. You'll also want to keep in mind that parts are printed upside down. That's because the print plate is oriented that way when printing. So you can optimize support structures to print with a tighter hold by upping the tip diameter. Under the support generator options, you can update the defaults from 0.15 millimeters to 0.5 millimeters. And this is going to increase the width so it holds objects more firmly, making print fails actually less likely. You can also add your own custom supports here to accommodate for any overhangs. Next up, we're going to need to slice the model up for printing. This is done through the Ember printer.
All right, so I think we got all that we need to find out about the Ember and the DLP process that it uses, and you can actually see that print in action. So it's pretty neat stuff. Let's talk about typical DLP characteristics, and I will point you back to the slide with typical SLA characteristics as a comparison. So the accuracy is at least plus or minus 25 microns. That's the same as the SLA. The resolution is as small as 39 microns. That's going to be a little bit better than the SLA characteristics. Layer thickness as small as 25 microns. The build volume is comparable. I think this is a little bit smaller. On the Ember, the machine that we just saw, the build volume was, or the surface area was about the size of a deck of cards. Of course, the height, the Z axis, can be much larger because you're just building in the Z direction, but the footprint of it is about the size of a deck of cards. Materials, again, photopolymer thermosets, nothing different here. And application area is the same. Conceptualization models, prototypes, casting patterns, so on and so forth. Here's some examples of DLP prints. These are rings that were created. So this would be used for casting patterns. So these rings would be made out of some kind of a wax-based material. That you can use a lost wax casting system, so you can surround these parts with another material for the mold, and then just burn out the wax, and you have replacement, and you have a nice metal part that we created by using these 3D printed casting patterns. You can see the fine detail on this, quite remarkable, and these as well, very detailed. I know from some of these photos it's a little bit hard to see, but especially when you compare it to the other printing processes. These are just phenomenal. Now, we're going to move on to the third and final type of that photopolymerization process we're going to look at in this lecture, and that is the clip process. CLIP stands for Continuous Liquid Interface Process. Okay, and this is one of the newer processes. It still falls under vat photopolymerization. We're still dealing with a liquid photopolymer resin that's being solidified through through exposure to light. But this is going to work a little bit differently, a little bit faster. And I found a video that I think is really instructive in this because, as I was reading about it a few years ago when it first came out, I was a little bit confused what's going on. So here, the tray in the bottom here, right? This is a bottom-up process. Okay, let me first say that. This is a bottom-up process. But there's a window across the bottom here that is going to allow UV light and oxygen to pass through. Okay, so it's not just a regular plate of glass. It's a special window that's going to allow light, of course, to penetrate, but also oxygen. The oxygen is the key here because it's going to inhibit the resin from solidifying and sticking to the window. All right. This helps to eliminate the peel process that we talked about earlier. The dead zone is the persistent liquid interface, and that's right here. All right. So that means that there's no solidifying, even though the light is being shown through here, there's no solidifying in the dead zone. And what that's going to allow is a flow, a constant flow of the resin as it comes down and through the dead zone, and then it's being solidified in this area just above the dead zone. Now, watch this video and you'll see, okay? So you can see this is the part that's growing, part being printed, and you can see the liquid down here, and it's being drawn under and solidified just above the dead zone, right? So let me play that again so you can see that, but you want to watch. The flow is on the left and right channels down here, and the liquid is flowing down, and it's flowing basically because of that suction as the part is being printed and the platform is moving up. It's creating like a suction effect, and it's pulling the liquid into that area so that it can be solidified. So let me play this one more time so you can see the flow through there. And then the printing as it's moving up. So this is really a remarkable video. When I found that, everything kind of became a lot clearer for me in terms of the process. Now let me show you kind of what's actually going on. I don't think there's any there doesn't need to be any volume in this. We're just going to watch the process. This is I can't remember whether this is sped up or not. Let's see.
So a bunch of scientists from a company called Carbon 3D just introduced a totally new kind of 3D printing. They were actually inspired to make it from the movie Terminator 2. Conventional 3D printing involves a printing head that passes over and over across a platform, depositing a thin layer of material each time. And this 3D printing forms an object continuously out of a liquid resin. So what's happening here is you have a bath of liquid resin that solidifies when light hits it. So the platform dips into this resin, and as it rises up, you have a projector underneath the resin pool that's projecting a series of cross-sectional images that are in the exact shape of the object you want to make. So as the platform slowly moves upwards, the projector moves through the different images, the different cross-sections, and that causes the object to form in the shape you want. Wherever there's ultraviolet light hitting it, that's where the plastic solidifies. So this could be a big deal because it's a lot faster than conventional 3D printers. It works in minutes instead of hours. Right now, 3D printing is still kind of a niche industry. People use it to make models or prototypes, but if this new 3D printer can be perfected, it could be possible for it to be used to make.
Okay, so we'll stop it right there. This is obviously kind of an older video because, spoiler alert, 3D printing and additive manufacturing has moved on from printing trinkets and chess pieces and all that goodness. But carbon is still around. Carbon is a major player in the clip process, the vat photopolymerization using the clip process. And those were some real times that printed in about a little bit over 6.5 seconds. So it's a phenomenally fast printing technique. The narrator kind of left out the big deal, which is the dead zone. And that's what that in the window, the special oxygen permeating window, allows this process to happen very, very rapidly. Now, is it the fastest process out there? Well, no, it's not. There's another process that's called intelligent liquid interface, which is basically, okay, so let me back up. Why do we have all these names? Well, we have all these names for these processes because as a company develops a process, they patent it. And so unless you want to pay Carbon a lot of money, you're not going to be able to make a clip type printer. You're going to even if you want to use roughly the same process, you need to name it something differently, and you need to have a slight variation on that. So one of these variations is the intelligent liquid interface. Okay, so let's play these videos side by side. So this is going to be printing the Eiffel Tower, and this is I believe this is real time. Okay. What's interesting is that it speeds up as it grows, and I think it speeds up because the cross section is getting smaller and smaller. So we'll see this right here. It's going to speed up, and of course you can see the cross section gets smaller and smaller of the Eiffel Tower because we're getting to the point, or the tippy top. All right, so again, 6.5 seconds, a little over 6.5 seconds. Now, if we look at the intelligent liquid interface, now the angle here is fantastic because you can kind of see the whole thing grow and it looks really freaky, but that's pretty fast. 4.5 seconds, okay, to make that sphere. Now, it's kind of not really a fair comparison because one, we're making the Eiffel Tower and the other, we're making a 50 millimeter sphere, but it gives you some sense of the speed with which these new printers can print. Now, speaking of speed, let's look at a printing speed comparison chart. Okay. And with these, you can see, okay, so this is the Form 2 is a laser SLA. So that means it's going to be a vector scan, mechanism. And you can see to make, let's just look at the sphere. Okay. So it takes 3 hours and 9 minutes to make a 50 millimeter sphere, what we just saw here. All right. 3 hours and 9 minutes. The Carbon clip process, which is basically DLP, but it's using that, that oxygen permeating window with the dead zone in there. It can make it in 1 minute and 45 seconds, which is quite an improvement over 3 hours and 9 minutes. But it gets even faster, right? The Unis, I'm not sure how to pronounce this, the Unis / and the Unis ZSL TV15. Unis is the company name, and they have a process called UDP. I'm not familiar with exactly what UDP stands for. Maybe one of you can look that up, but you can see that this process, and by the way, I've continued to look this up. These printing comparisons are, the tables are a little bit old, but the Unis ZSL still is the fastest in the world. So the 50 millimeter sphere, we can improve that with the / by 30 seconds. And we can practically take off a whole minute with the Unis ZSL. Okay. So that is a, remarkably fast printing process. Less than 30 seconds to print a 50 millimeter sphere with the Unis. Okay. So here's just some comparisons so that we can kind of see. So, resolution, right? 150 microns for the Form 2 SLA, 100 microns with the DLP, and the clip from the Carbon is 75 microns. So the resolution is getting better, right? A lower number means a smaller scale resolution. The slash, which is one of the faster ones, is comparable. Notice that this slash is a little bit larger back up to the Form 2 SLA. And then the real fast one is kind of in between, 89 microns, right? The Z resolution in micrometers, this is micrometers, not but micrometers. That's basically the layer height, right? The layer height. So the carbon has a phenomenal layer height, 1 micron thin for the layers. That is astronomically, that's like on the layer thickness equal to a hair. 10 microns for all the unis is not too bad at all. The moon ray is 5 and the SLA Form 2 is 25. So, and you can see the prices, right? The carbon is $250,000. That is not a home printer by any stretch. Now, Carbon was one of the manufacturers that was printing shoes and stuff using their clip DLP process. And so they're more industrial grade. The Unis slash is up there. Certainly not $250,000, but it's still just a smidge under $10,000, $7,500. So it's not something that you and I can go out and buy. All right. The last quip I'll leave with you is just a little race. So let's see how this works. Unfortunately, I can't cook these at the same time, but I'll try to cook them very quickly together. Ready, go. And the Pro 3D is done. And we're still, even at 7 times the speed, we're still getting started on the carbon. It seems like it takes forever when you're comparing it to the Intelligent Liquid Interface new Pro 3D. But, you know, this is still phenomenally fast, certainly compared to your run-of-the-mill 3D printer, especially the ones with the different processes. The powder bed fusion machines with the laser and the metal powder take comparatively ages to print. All right, so that is the end of the slides here. The last thing I want to kind of show you here is a little bit more about how the Carbon 3D printer works, because it's an important process. So this is going to be the last slide here. Okay, so here you can see how we're having the mask. Remember, this is the mask projection system. And it's going to shine up and it's going to flash each layer individually. And as the build platform moves up, the oxygen is going to permeate this special window to keep the resin from sticking. And then the part is finished and the pins are removed. All right. It looks like this was making some kind of electrical connector. All right, so I will see you in the next topic, which I believe is going to be material extrusion.